Today we're going to start off with a couple of simple questions. The first one is if you had x plus 3 equals 8, what are all the things that x could be to make this true? And the other one I'd like you to think about is if we have x plus y equals 5, what are all the things that x and y could be to make this true? So I'm going to give you a few minutes to think about that. You can pause the video if you like, and then we'll come back and see what you did. Okay, let's see how we did. This first one, we had x plus 3 equals 8. X could be 5 because 5 plus 3 is 8, and that's it. X can't be anything else, so you just have that x equals 5. You probably already figured that out as soon as I wrote the question down. How about the second one, x plus y equals 5? What could x and y be? Well, hopefully one thing you said was that x is 2 and y is 3. But you also should have said that x equals 1, y equals 4. You could have actually reversed these. X could have been 3, and y could be 2, and x is 4, and y is 1. And most people will get at least 2 of those, if not all those combinations. But I'm wondering, did you also get that x equals 0 and y equals 5, and the reverse of that? Did you try any negative numbers? So for example, x equals negative 7 and y would equal 12. Or maybe x equals negative 2 and then y would be 7. Wondering if you tried any fractions. So did you have something like x equals a half and y is 4.5. And so you can see here that we could actually have an infinite amount of solutions. I could keep going all day long. I could do combinations of negative numbers and fractions, and just really there's an infinite amount of solutions here. And so what do we do with that? When we solved an equation like this over here, we could just write the answer down. But here, I could do this, and then I can keep going forever and never stop. So how do I actually know what this solution is? Well, that was a question that a mathematician hundreds of years ago was thinking about, and his name was René Descartes. And he was a French mathematician, and he wanted to be able to actually have an infinite amount of solutions and just see them all. And you can't do that by listing them. So he came up with this other system of figuring out what the solutions to an equation were when you have two different variables rather than just one, like over here. He came up with this coordinate plane. It's also called the Cartesian plane, named after René Descartes, because that's what his name was. I guess if you invented something, you'd probably name it after yourself too. Okay, let's take a look and see what he wanted to accomplish here. So let's go ahead and look at our original solutions to x plus y equals 5. Okay, so what he said was, is that just like on a number line, you can find all the numbers on a number line. He had this line going across here be the number line, and it was the number line for the x values. So really, even for this first one, x equals 5, we could draw a number line and put a dot on 5 to show the solution. So we can see it graphically, but where this dot is, but that's not really much more use. It's just as easy to see x equals 5 than it is on a number line, okay? But here, that x number line is just like the number line that we're used to having when we solve for x. And then on this axis here, this is going to be a number line that's going up and down, more like a thermometer, but it's going to be our y's. And so what he did was, he said, well, for this first solution, we have x equals 2, y equals 3. And so here's 2 on the x-axis, here's 3 on the y-axis, and where those two meet, he's going to put the point here. So this indicates that it's the point 2, comma 3, and we could write that even as 2, comma 3, where this is the x and this is the y. But really what this represents is the solution to this equation here. We have x equals 1, y equals 4. That's going to be 1 on the x and 4 on the y. We're going to have 3 on the x and 2 on the y. 4 on the x, 1 on the y, 0 for x, so I don't even go left or right at all, and then I'm going to go up 5. Here we have negative 7, 12. I can go to negative 7 and 12, but I think it's going to be off of my chart. Let's see, 1, 2, 3, 4, 5, 6, 7. This goes up to 10. So it still exists. It's just going to be like somewhere up there, the second dot up there. But we do have negative 2, 7, negative 2, 5, 6, 7, 1 half, 4 and a half, and so on. So what we can do is we can graph all these solutions to the equation here. And even though there's an infinite amount of solutions that we see here, we notice that when we graph them, we see a pattern. They aren't just randomly put all over the graph. In fact, there's a specific relationship, and that relationship is this, that they always have to add up to 5. And what Descartes discovered was that you can actually see that relationship. And so what we can do is once we get enough points where we can see what that pattern is, we can actually, instead of drawing individual points, we can draw an infinite amount of points. And we can do that by making this line. So I'm going to try this over here. And my marker's kind of big, so we'll see how it goes. There we go. So by drawing that line, a line is made of an infinite amount of points. So when we said here with our solutions that how are we going to draw an infinite amount of points or an infinite amount of solutions, we just did that right here. And in fact, by putting arrows on the end, this indicates that this goes on forever in both directions. So you can see it actually would go through this point here, but could also go up to points in the millions or billions or whatever. It includes all the fractions, all the decimals, all the negatives, everything possible on here. So you actually just showed an infinite amount of solutions for x plus y equals 5. And we can test this out in a couple of different ways. One thing was that we didn't list all the points here, but I could have listed something like x equals negative 1. And if x was negative 1, what would y be? Y would have to be 6. And sure enough, if I look at my graph, negative 1, 6 is right there. So even though I didn't figure it out, I still had that point right there. Likewise, we could use it backwards. This is a point up here. And if I can find the coordinates of this point, what its x and y are, let's see, that would be negative 1, negative 2, negative 3, negative 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the point negative 4, 9. And sure enough, if I add negative 4 plus 9 together, I get 5. So every single point that I can find that's on this line, if I add up those two numbers together, it's always going to equal 5. So first, let's take a second to look back at what we worked on before, which was x plus y equals 5. So if we randomly just try to figure out what equals 5, some are easy, but some are a little more challenging. In fact, when I try to pick those negative numbers and positive numbers, it took a while to make sure that I had the correct solution there. But what we can do, though, is we can rewrite this equation by subtracting x from both sides. And so this equation is actually the same as y equals 5 minus x. And what this means is that instead of trying to pick an x and then try to guess what plus x is 5, we can just put the x here, do simple arithmetic, and figure out what y is going to be. And so usually what we do is we keep track of this in an xy chart. And so what I'll do is I'll put x up here and y here. And I'll just pick x and then solve for y. Now, a lot of this is easy to do mentally for one like this, but I want to do it on an easy one. This way you see how it works. And then when we do more complex ones, you'll be able to do it more easily. So let's say we said x was 2. You already knew 2 plus 3 is 5. But if I change this x to 2, this will say 5 minus 2. So when you said y equals 5 minus x, I'm saying y equals 5 minus 2. I'm changing the x to 2. And then I have y equals, and I can simplify 5 minus 2 to get 3. And so it literally tells us that y is going to be 3. Okay? Let's say if x is 1, how would that look? Well, we'll say that y equals 5 minus 1. So y equals 4. And then when we had a little trickier one, like when I picked x to be negative 7, for example, we can do y equals 5 minus negative 7. And when we subtract a negative, that's the same thing as adding the opposite. So we get that y equals 12. And that's a lot simpler to be able to do. And then we just graph those points. And once we have enough where we feel confident of the pattern, then we can just use a ruler if it's a straight line, or we would always make a smooth curve if it's a curved line to see what the actual graph is going to be. And we can always pick more points. There's not really a right way to pick to know which points to pick. Usually I pick a few positive numbers. I almost always pick 0, pick a few negative numbers, and maybe a fraction, just to kind of make sure that you have the pattern filled in all the way. And then once you feel comfortable with that, maybe there's a part that you want to kind of zoom in on or get something more specific, then you can pick X's that will work a little bit better there. So let's y equals x squared minus 3. Okay. So we'll make our xy chart. And we'll start by picking x's and solving for y. Now, when we square numbers, they're going to get big pretty quickly, and my graph only goes up to 10. Normally, you could have a graph any size you want, but for most of the ones that we practice and that we're really interested in, they're going to be kind of smaller. In other words, the ranges will be around between 10 and negative 10, both for the x's and the y's. So let's go ahead and see what we can do here. So let's pick a number for x first. Let's just start with, let's let x equal 4. Okay, so if x is 4, that means we change the x in the equation to 4. So instead of having x squared minus 3, we have 4 squared minus 3. We'll use our order of operations to get y equals 13. Now that's fine. I have the point 413. My graph only goes up to 10, however, and so I want to make sure I pick some x's that are going to be smaller than that now to make sure that they actually fit on the graph. So let's pick 3. Y equals 3 squared minus 3. That's 9 minus 3. 9 minus 3 is 6, and that will fit here. Now you can do this mentally as well. You don't have to write down all the steps, but if you can just do it in your head, for example, if I pick 2, and you can think, oh, 2 squared is 4, minus 3 is 1, no problem. Go ahead and do that. Sometimes, though, it gets a little tricky, and you want to make sure you're doing it properly, so writing it down is always a good idea. We did 4, 3, 2. Oh, let's go ahead and do 1. 1 squared is 1, and 1 minus 3 is negative 2. Let's let x equal 0. 0 squared is 0. 0 minus 3 is negative 3. Let's do a negative now. Let's go down to negative 1. Negative 1 squared. Now that's going to be a little trickier. I will write that down. When we write that, especially when we should do it all the time, but it's extremely important to do when we have negative numbers, is that we want to put that in parentheses because we want to make sure that we're doing our order of operations correctly. So here we're squaring all of negative 1. If I wrote it without the parentheses, it would look like this. And if you put this in a calculator without putting this in parentheses, you're going to get the wrong answer because it's only going to square the 1 and then take the opposite afterwards. But we actually want to square all of negative 1. Negative 1 times negative 1 is positive 1. Minus 3 is negative 2. Extend this a little bit. Negative 2. So we're going to have y equals negative 2 squared minus 3. Negative 2 times negative 2 is positive 4 minus 3. And 4 minus 3 is 1. Now we might notice something here that we're actually seeing the same number show up again. Notice here when I did 2 and negative 2, I'm still getting the same y coordinate. And a good thing to do when you make these charts is to look for patterns like that. So why would that be happening? Well, when I square 2, I'm getting 4. And when I square negative 2, I'm getting positive 4 as well. So I'm going to get the same result here. So what's going to happen when I square negative 3? Well, squaring negative 3 is 9, but squaring positive 3 is also 9. So I'm going to have the same result right here. Let's start to plot these points. So I'll start with 3, 6. 2, 1. 1, negative 2. 0, negative 3. Now I have -1, -2, -2, +1, -3, +6. Now this is definitely not a straight line. And in fact, we could connect these with all straight lines, but that actually won't work. And here's why. If I connect these straight across right here, between here, that means the point 1/2, -2.5 should be on the graph because it would be right in the middle. But if I put 1/2 in my chart here, what happens when I square 1/2? So we have y equals 1/2 squared minus 3. A half times a half, that's a half of a half, which is a quarter minus 3. And a quarter minus 3, well, that's the same as 3 minus a quarter, but it's going to be negative. So that would be -2 3/4. In other words, it's going to be a quarter bigger than -3. So it's -2 3/4. So that point is actually going to be down here. It's not going to be at the halfway point. And so this is what I said before about you want to make a smooth curve. And you know what? I'm a little off here. This should be right here. I just noticed that. I'm sideways a little bit here, so it's hard to tell a little bit. So we're going to end up with this pattern when I do this here. Ooh, well, it's not bad. I kind of missed this point right here. It's supposed to go through there. And I'm going to put arrows on the end to indicate it's going to go up in both directions. But this is the general shape of the graph. And when you do it on your own, you can be really careful and make sure to get all the points as correctly as possible. So this is what y equals x squared minus 3 actually looks like. And in fact, it keeps going up. And if I kept it continuing up, it eventually would go through this point here of 413. So you can see it's getting steeper and steeper and steeper as it goes. And it probably would go through a point that's right about there. So this is what all the solutions to this graph looks like. And that's what we really want to remember, is that I could pick any point on this graph, no matter how much of a decimal or how negative it is or anything. And if I find the coordinate of it and I replace the x and the y with those x and y coordinates, that's going to make it true. So in other words, these are all the points, these are all the solutions to this equation. We're just seeing it visually. So that's how we can do graphing. And really all graphing is finding the solutions to an equation where there's two choices. And you're finding all the different combinations that make up the solution to the equation. And then we're using this coordinate grid here to actually plot the points, to actually visually see what those solutions are. By making the line or the curve, we're actually graphing an infinite amount of points, and we're using the idea that there's a relationship, that we see that pattern to see the pattern. And once we have that pattern down, we can put arrows on the end to indicate that pattern is going to continue forever, and we have graphed the equation, which means we found all the solutions. So now on your own, I'm going to put a few equations on the screen, and you can go ahead and solve them by making XY charts to find X's and Y's that will work. And then when you're done, you can go ahead and graph them. To check your work, you can go online, or maybe on your computer you have a graphing program, and you can go ahead and just type them in and see if you've gotten them correct. If you've plot points and there seems to be a couple that are out of place, like on my graph here, where I was looking at it after a second, I was like, wait a minute, that point doesn't fit this this nice pattern. It kind of went off to the side there. Then go ahead and check your chart to make sure you've done the points correctly and that you've graphed them correctly. So I hope you have fun with that, and enjoy.